Okay, welcome back. So we'll continue with the material on inferential statistics, right? Now that we have the basic framework established, where we talked about the central limit theorem and its applications, now we can move on and start talking about what we can do with this, right? So this is where we really take off into inferential statistics, where we use the sample data to say something about the population parameter, right? So confidence intervals are a dominant way of establishing bounds around population parameters using sample data. So what does that mean? How does it work? What is the logic behind it? How do we calculate these things? That's what we'll do in the next couple of sessions, right? So in this session, we'll just do 6.1, where we will talk about the basic case, right? The most basic case is where we're trying to establish a confidence interval around the mean when the population standard deviation is known, right? This is an abstraction. In general, we don't really know the population standard deviation because we don't understand the population itself. We can't study the population itself. Where does this number come from? Now, you can get around it a little bit by saying, okay, you have some prior studies or you have a large data set where the approximation is pretty close, and then you can assume that the population standard deviation is known. But that's kind of, a level of, just waving your hands about and asking you to take it as an article of faith that the population standard deviation is known. Okay, but that's the basic case. So we'll try to establish how to find the confidence interval for the mean when the population standard deviation is known. Then we'll relax that assumption. That's the more general case. So that's what we'll do in the next session. And then we'll talk about how do we establish population confidence intervals around two other kinds of statistics, summary statistics that we calculate in general, around proportions and around variance and standard deviation, right? So that's what we'll try to do. Okay. So if you want to really think about the delineation based on what we did in chapter 2, this is basically establishing confidence intervals around central tendency. This is establishing confidence intervals around position, and this is establishing confidence intervals around variation, right? So when we talked about summary statistics, when we started off this course, we talked about three big measures of summarizing the entire data set. One was around central tendency, around typical values inside the data set. One was around relative positions, which is measured by proportions, and then around variance and standard deviation. Okay, around variation. Okay, so let's start with the basic case. Let's talk about how do we find confidence intervals for the mean when this is the case when the population standard deviation is known. Okay. So we'll talk about a few key ideas. So this is the first time you're looking at confidence intervals. So it's important to get the definitions right. So we make sure that we know all the definitions and what it is that we're talking about. What do we mean by point estimates, margins of errors? What exactly is a confidence interval, and how do we uh, find it? And then we'll talk about its stories around how do we know what sample size will is sufficient to be generally confident in our estimation process. Okay, so let's go in and let's talk about first of all the prior uh, definition, the notion of a point estimate. Okay, a point estimate in a very simple sense is your best guess about the population parameter. Okay, so it's a single value estimate. It's a point. So first of all, it's an estimate. An estimate means that it's an approximation. This is our best guess for whatever it is that we're considering. And the point portion says that it's one single estimate. It's not a range of values that we assign to it. It's just one single value that's assigned. Right? So a single value estimate for a population parameter. This could be anything, right? If the population parameter is the mean, then you can get a point estimate for the mean. If the population parameter you're considering is variance, then you can get a point estimate for variance. With standard deviation, you can get a point estimate. But the crucial thing to recognize is with a point estimate, we're trying to essentially estimate something about the population, a parameter, something that we like to measure about the population using the sample information. Okay. So if you think about what the point estimate, what the unbiased point estimate for the population mean is, for the average inside the population is, what do you think could be the single best guess that I have? If I have to put one value and have to guess at what the population average is, what is the single best thing I can do? Right? If I have nothing else to go by, I can essentially draw a sample from that population, calculate the average inside the sample, what we call the sample mean, and use that as the single best estimate of the population mean. So if I wanted to study the population mean, I didn't know anything about the population mean, what do I do? Intuitively tell yourself the story, right? I won't know the average inside the population. There's no way for me to study the entirety of the population. The best thing I can do, most reasonable thing I could possibly come up with, is to say, let me just get a sample out of this population. Look at the mean inside that sample. So this is the sample mean. X bar represents the sample mean, and use that as my best guess of what the population mean should be. Right? That's what we mean by a point estimate. Right? For instance, here's an example. So you're a researcher and you want to collect data about grocery store employees in a county, right? A county employs you. You want to collect information on what the income looks like, on the number of hours worked by your grocery employees within the county. Now we have one of two options, right? One of two options. One option is to look at your county, define the county properly, and find every single grocery store employee who works inside that county. Go to them, each of them, ask them how many hours do you work in a typical week, collect all of that information, and then average across all of those data points to get the population mean. Right? That's your first strategy. Now, as you can imagine, this is crazy. This is like you have to find, if it's a large county like Hudson County or whatever it is, if it's a large county or Westchester, any kind of large urban conglomeration, there are going to be thousands, if not hundreds of thousands, of grocery store employees possibly within that county. All right? And you're just one lonely researcher that you really can't go around collecting this kind of data set on your own. So, what is your next best alternative? The next best alternative is to reason, and it's intuitively reasonable to say, okay, most grocery store employees are not going to, I'm not going to see a lot of variation in the number of hours worked, right? I mean, there's going to be variation, but it shouldn't be a whole lot. So it doesn't really make sense for me to expend all of this effort to try to find every single grocery store employee, because there's going to be a lot of overlap, right? So the range is going to be fairly narrowly defined as the number of hours worked. So maybe what I can do is, instead of going out off into the wilderness and trying to study the population as a whole, I collect a sample out of that population. So I essentially look at a sample of 40 employees from several grocery stores in the county. So just to hedge my bets, I don't concentrate on one grocery store. I just go to a bunch of grocery stores randomly spread out across the county, choose a few of them at random, few of these grocery store employees at random from each store, and I form a sample of 40 employees. And then I collect the information on those 40 employees, and I have this data set, a sample data set available to me. So for each of those 40 employees, I have information on the number of hours they claim to have worked in the past week. And now based on this, I could say, okay, what can I say? I can calculate the mean inside this sample, right? The average number of hours worked within the sample. So if x bar here is the sample mean, and it tells me that if I sum all the values divided by n, the average number of hours worked for my sample is 29.6 hours, right? So as you can see, there's a lot of variation there, but it's fairly closely bound, right? So you can find like about 39, some grocery store employees work about almost a full-time uh, uh, gig, so 39 hours a week. Some work much fewer hours, maybe 2 or 3 days a week, so on and so forth. There's a lot of variation inside the sample itself, but the average is about 29.6 hours per week, right? So if I had nothing else to go by, and I ask you, okay, based on what you're seeing inside the sample, what is your estimate? What is your best guess of what it would what it would look like for the population as a whole? The population here is all the grocery store employees within that county. Your single best guess is to say, all I can go by is the numbers I'm seeing inside the sample, and the sample average is 29.6 hours a week. So my best guess is that the population average is also about 29.6 hours a week. This is not to say it's right. It could be completely off the mark. You might just have some kind of bias in the sample itself, but this is your single best guess at this point as to what the population average could be based on what you're seeing within the sample itself, right? So that's what we mean as a point estimate. So the point estimate for the population mean here would be the sample mean. Okay. All right. An interval estimate essentially says, okay, so if I really stop and think about this for a second, the point estimate is giving me an estimate of the population mean based off a single sample. Now, straight away, that should give you a pause, right? Because your analysis lives and dies by the strength of that sample. If for some reason that sample is atypical, if some reason the sample is not representative of the underlying population, if for some reason the sample is too small, whatever the issue is, that you can't have a whole lot of confidence that the actual population mean is very close to the sample mean, because all you have is information on 40 employees chosen at random from a few grocery stores, and you're using that estimate to say something about the entirety of the population of grocery store employees, and that straight away you should be questioning whether that's a good enough estimate. Okay, so an interval estimate is a second way of thinking about this, is to say, if I take multiple samples, each of those samples is going to give me a different mean, right? So in one sample, I might see the average is 29.6, like we saw. If I collect a second sample, maybe it tells me that it's 30.5. A third sample says it's 32.1. So I might get a range of different values. So that's what the interval estimate says, is that, okay, so instead of using a single point estimate, why don't we estimate the population parameter using a range of values? So if we have a range of values, we can be more confident that the population mean is within that range, right? When it's a single point estimate, our level of confidence in how close the point estimate is to the actual population parameter is, excuse me, it's fairly limited, right? So instead, to gain a little more confidence in our analysis, we essentially use an interval estimate, and that's basically the logic behind a confidence interval. Okay, so a confidence interval asks the question, how confident do you want to be that the interval estimate that we're coming up with, so we come up with a range of values, so it has a left endpoint and a right endpoint, so it's a range of values, well-defined range of values. How confident do we want to be that the population parameter is somewhere in this range, that the true value that we are after inside the population is somewhere within this range, that and the range is constructed using sample data. Okay, that's what we mean by a confidence interval. And the first thing we need to understand when we talk about a confidence interval is what we define as the level of confidence. Okay, the level of confidence is usually represented as C. When you see this letter C in statistical analysis, it's usually representing the level of confidence. So the level of confidence is essentially telling me the probability that the interval estimate that I've created, the range of values that I've created, contains the true population. Okay, contains a true population parameter. Okay, so for instance, what C is, in a very precise way, C is going to tell me what is the area under the standard normal curve. So what is the area under the standard normal curve, within which range about C% of the area is collected, right? So we'll talk about examples, and that will make things clear. But that's basically the theoretical construct. The theoretical construct is that if I want to be this level, if I want to make sure that the population parameter is within this range, what is the area under the standard normal curve within that range? And that tells me the level of confidence I have that the true population parameter is within that range. Okay. So one thing to recognize here is that if this is C and the distribution is symmetric, then the area here should be 1 minus c. So the leftover area, the area between this unshaded area plus the area in this unshaded area, together the remaining area in the tails should be equal to 1 minus c, right? So the area in this unshaded region here plus the area in this unshaded region here should be 1 minus c, because the area in the shaded region is c, the remainder is in the tails. Okay. All right. So if that's the case, then if I think about what the area is in each of these tails, so if the remainder is 1 minus c, then half the area is going to be in the left tail and half the area is going to be in the right tail, right? So if the remainder is 1 minus c, 1/2 of 1 minus c, so half of 1 minus c is going to be in the left tail and half of 1 minus c is going to be in the right tail. All right. Okay, so when we talk about confidence levels and confidence intervals, what we mean is that if we say that the level of confidence is 90%, right, as it says, if we establish that the level of confidence, if we want to be 90% confident that the interval that we've created contains a true population mean, that's what the level of confidence is saying, right? If the level of confidence is 90%, that's what it means, that we are 90% confident that the interval that we formed using the sample data actually contains the true population B. Okay. So for a 90% confidence interval, what does it mean? The area between these two critical values that we call, right, the endpoints on the standard normal distribution, how many standard deviation steps away from the mean can I be on the left and right end, such that the area between those 2 points is exactly equal to the confidence level, which is about 90% here. C equal to 0.90 is a way of saying that the interval is formed at the 90% confidence level. So if this is 90%, the remainder is 10%, the remaining area is 10%, half of which is here, so 5% is in the left tail and 5% is in the right tail. Okay? So if I want to know the critical values here, I want to know what these endpoints look like, what would I do? I would just go into my standard normal table. I would look for 0.05 in the body of the table. So it tells me that the area to the left of this Z critical value is 0.05. So I go looking inside my standard normal table, find 0.05, and the Z-score attached with 0.05 is negative 1.645. So that's the left cutoff for the confidence interval. Okay, and similarly, because it's symmetric, if this is negative 1.645, then this is going to be positive 1.645. All right, so it tells me that within 1.645 standard deviation steps from the mean on the left and the right end, about 90% of the distribution is basically covered. So I have a 90% probability that the true population mean will lie within 1.645 standard deviation steps from the mean. Okay. All right. The next thing, I hope that's clear. I mean, all of this will become clear once I show you some examples. Will become much more cogent once I show you some examples. Is basically the theoretical bit of the uh, discussion. Okay? So there is a story about what we call the sampling error. The sampling error is, as usual, if you think about what the error is, this is what you're saying. This is your estimate. The sample mean is your estimate of the true population mean. This is the actual true population mean. The difference between your estimate and the actual reality, the true value, how far that is, measures sampling error. Okay. So for the mean, the sampling error is the difference between the sample mean and the true population mean. But in general, we can't really tell what the true population mean is. So in general, mu is generally unknown, so we don't really know the true population mean. But if we did know the true population mean, or if we had a reasonable um, alternative way of measuring the true population mean, so the difference between what your sample is saying, the sample mean is saying, versus what the true population mean is, that difference is what we call the sampling error. Okay. Okay. The margin of error is one crucial element of this. So the margin of error is going to say what is the greatest possible distance that we can have between the point estimate and the value of the parameter and the true value of the parameter. What is the largest possible sampling error that we can have for a given level of confidence? For a given confidence level, what is the maximum we can have? And the margin of error here, E, essentially tells me that if this is the standard deviation, right? So intuitively step through this way, right? So this is the standard deviation of the sample means, right? It's telling me the standard deviation of the sampling distribution. ZC tells me how many standard deviation steps I can be away from the mean and still be within that confidence range, right? That's what ZC in this case was establishing. ZC is telling me how many, listen to the wording carefully. ZC is telling me how many standard deviation steps, the number of steps, standard deviation size steps I can be away from the mean and still be within this range, right? So if that's the case, so if this is the number of standard deviation steps I can be away from the mean and still be within that confidence range, and this is the size of each step, this is the total distance I can be away from the mean on either side and still be within the confidence interval, right? I mean, this again, if you want to really understand this, this tells me number of steps. Okay, if I can write it properly, this is going to tell me the size of each step, right? So it tells me the number of steps. The z-score is telling me how many steps I can be away from the mean and still be within the confidence interval. The standard deviation is going to tell me the size of each of those steps. So the number of steps times the size of each step tells me the total distance I can be away from the mean and still be within the confidence interval. Right? So the margin of error is telling me how far can I be away from the what is the maximum size of the sampling error that I can have and still be within that level of confidence, right? Given level of confidence. So from the central limit theorem, we know that ZC, the sigma x bar, the standard deviation of the sample means, is the same as the population standard deviation over the square root of the sample size. So we can substitute that. Okay. All right, some conditions on when this can happen. The sample needs to be random. Obviously, you can't select the sample in some systematically biased way. The population needs to be normally distributed, or the sample size needs to be greater than 30. That's basically the conditions for when the central limit theorem holds. For us to go from here to here, we need to utilize the central limit theorem. And for the central limit theorem to actually hold, we need to know if the population is normally distributed, or we need to be confident that the sample size is sufficiently large enough for the results of the central limit theorem to go through. Okay. Okay, this is also sometimes called the maximum error or error tolerance, or there's a whole bunch of different terms, but the standard way we call standard terminology in this case is to call this the margin of error. Okay. All right. So here's a quick example. So here's where we'll start looking into examples just to fix ideas. So how do we find the margin of error? Right. So we have the data about the grocery store employees, and suppose we want to have a 95% confidence level. So where is this number coming from? This is at the discretion of the uh, researcher, right? How confident you want to be in your estimation is dependent on you. So the usual uh, uh, well, the most prominent confidence level that's generally used in analysis is the 95% confidence level, but you can choose it at any confidence level that you want, right? The usual ones are 90%, 95%, and 99%. That's what the usual confidence level estimations are reported at. Those are known as the 10%, 5%, and the 1% significance levels. So usually those are the three estimates, but in general, the 95% confidence level is the most common one among these. Okay. So suppose I want to be 95% confident that the interval estimate that I'm coming up with, the interval estimate that I'm coming up with contains a true population mean. This number is given to me on an exam, on a question. This number is given to me. In a more realistic case, you would choose that number ahead of time, right? You would choose what level of confidence you want to do the analysis at. Okay, so suppose we want to find the margin of error for the mean number of hours worked by the grocery store employees. And here's the crucial thing: assume that the population standard deviation is known. Right here, we know the population standard deviation. This is sigma. Sigma is known in this case. Okay. Okay. So to calculate the margin of error, we need two pieces of information. We need sigma, which is given to me, and we need to know ZC, the critical value. Okay, we know the size of each, we can calculate the size of each step. We need to know how many steps we can be away from the mean and still be within the confidence interval. So if this is a 95% confidence interval, we need to be in this range of ZCs such that the area in between those two critical values is 95%. Okay, if this is 95%, then the remainder is 5%. What's left over is 5%. Half of that 5% is in the left tail, and half of that 5% is in the right tail. So this is 0.025. So 2.5% is here, and 2.5% is here. Okay. So to find this critical value on the left tail, negative ZC, all I have to do is I go into my standard normal table, look for 0.025 in the body of the table, and find the critical value which is associated with it. And if I go look that up in the table, the critical value which is associated with it is about negative 1.96. Okay. So if this is negative 1.96, this is positive 1.96. So what this is telling me is that I can be about 1.96 standard deviation size steps away from the mean on the left and the right and still be within this 95% probability level or confidence level. Okay. So now that I know what ZC is, the second thing is to know whether I can use the central limit theorem or not. In our particular case, we had 40, the sample size was 40, which is greater than the threshold that we set of 30. So we can use the limits of the central limit theorem. Okay. All right. So to find the margin of error, we need the two pieces of information. We need to know how many standard deviation size steps can be away from the mean. We found that that's 1.96. Right, again, this is how we found 1.96 from the previous slide. And then we needed the size of each of those standard deviation steps. And if you use the central limit theorem, this is sigma over square root of n. Sigma is given to be 7.9. N here is the sample size, which is 40, square root of n. So the margin of error is 2.4. Okay. So you are 95% confident that the margin of error for the population mean is about 2.4 hours. So if I form an interval estimate around the sample mean with about a tolerance of about 2.4 hours on either side of that sample mean, I can be 95% confident that the true population mean is in that interval. Okay. So in general, if I had to form a confidence interval around the population mean, okay, so this is around the population mean, around the population average, I first calculate sample means x bar using what I have inside the sample, and then I form a margin of error where the margin of error is given by ZC times sigma over the square root of n. So the true population mean, the interval for that level of confidence, for level C confidence, that the true population mean is within this interval. Okay. All right. So I have a recipe book here. So these two slides tell you how to do a recipe. First, we collect samples, find the population to estimate the confidence interval around the population mean. First, you start with the sample information. So first you find the sample mean, which is straightforward. You collect the sample and calculate the average within that. Then you find the critical value. Then for a given level of confidence, you find the critical value ZC using the standard normal table. Once you have the critical value, you can find the margin of error using this formula where ZC times sigma over the square root of n. This is a case where this population standard deviation is assumed known, right? Once you have that, you can find the confidence interval. Okay, so all of this is theoretical. Fine, let's look at an example, and I really hope this is where all the ideas fall into place. Okay, all right. So you're a researcher. Okay, you're sitting here. You're working for a college administrator, and your boss comes to you, and they want to figure out what is the mean age of all students who are currently enrolled. Right? You want to figure out what is the average age of all students who are currently enrolled at the college, right? So you have one of two options, right? One thing is to find every single student who's currently enrolled at the college, go up to them, first find them, then go up to them, then ask them what is your age, collect that information, and then average across all of those numbers, and then you can answer this question. It's going to take a long time for you to do, right? It's going to take weeks, if not months, to find all of these people, ask them what their ages are, collect that information, put it into a database, make sure there are no errors, and then to calculate a single simple summary statistic like the population average is going to be a massive undertaking. But you're smart, you've taken a statistics course, you know that you don't need to do all of this. What you need to do is to just go look at a sample. Okay, so you just walk out of the office, you collect, randomly students are walking around in the quad outside the office, and you stop 20 students and ask them what their ages are, right? So you form a sample of 20 students, and then you find the average age within that sample is about 22.9 years, right? So you calculate the average age within the sample. So this is what your X bar is going to be, right? So if you didn't know any better, you would stop there. You go back to the admissions director and say, so, I talked to 20 odd students who are walking around. Their average age is about 22.9 years, and that's my best guess that the average age of the population is about 22.9 years. Now, the admissions director is going to look at you and say, but that's just randomly selected 20 students. You have only information on one sample. How confident can we be that this is actually the true value inside the population? So at that point, you say, okay, that makes sense because this number is coming out of this random sample of 20 odd students that I collected. How confident could I possibly be? Not very. So then you recognize, oh yeah, so what I can do is that I can try to establish a range of values around which I can be confident. Okay? Alright, so from the past studies, what we found is that the standard deviation is 1.5 years. Here I'm just playing God, I'm just giving you the population standard deviation. In the next session, we'll consider the case where that's not known. In this case, the population standard deviation is known, and we also know somehow that the population is normally distributed. Okay? Two big assumptions that we're making, but go with me here. You set about trying to be 90% confident in your interval estimate. So you'll set your confidence level at 90%. So you're okay with making an error about 10% of the time. That's what it means to be 90% confident, that about 10% of the time that you're going to make an error there. Okay. So how do I form this confidence interval? Okay. So first question is, for me to be within a 90% confidence level, right? For my confidence level to be 90%, the area between the z critical values, negative zc and positive zc, needs to be 90%. Okay? So if this area is 90%, the leftover area is 10%, which means 5% is in the left tail and 5% is in the right. Okay? So then I go to my standard normal table, look up 0.05 inside the body, inside the area section of the standard normal table, and it tells me that the critical value here is negative 1.645 and here is 1.645 on the right. So what this is telling me is that if I go 1.645 standard deviation size steps to the left or to the right of the mean, I can still be within this region here, which means that I can still be 90% confident. 90% probability is distributed in that region. So now I have my ZC critical value. Okay. Once I know ZC, I can go ahead and find the margin of error. How do I find the margin of error? I can use the central limit theorem. So I know ZC, this I found from my standard normal table. Sigma is given to me. Sigma is the population standard deviation. And I know my sample size, which is 20. So I can form the margin of error, 1.645 times 1.5 over the square root of 20. So the margin of error is 0.6. So understand what the margin of error is doing. It's taking the number of standard deviation size steps, multiplying that by the size of each of these steps, sigma over the square root of n. So it's establishing the total distance I can be away from the mean and still be inside this region. Okay? So I can be 0.6 units away from the mean on either direction and still be within that confidence level, right? So the confidence interval, the left end point is that, okay, I know the average inside the sample is x bar, which is 22.9, minus e, right, which is, I'm trying to find the left end point. So I can start at the mean and I can be this distance away from the mean, from the sample mean, and still be within that range, 22.3. And the right end point is x bar plus e, so 22.9 is the sample mean, plus 0.6, which is the margin of error, and this is 23.5. So I can be 90% confident that the true population mean is between 22.3 and 23.5, right? So I can now be reasonably assured that I am at a 90% confidence level. With a 90% confidence, I can say that the true population mean is within this range of 22.3 and 23.5. This is all based, first of all, on the point estimate. The point estimate is 22.9. So the sample mean is 22.9. And I recognize that I can't just hang my hat on the point estimate. So I say, okay, I can't really be all that sure that the point estimate is a really good estimator of the population mean. So let me make an interval around it. By making an interval around it, I can be more confident on a range of values than I can be on a single value. I can be more confident on a range of estimation rather than on a single value of estimation, right? So the way I form this range is to essentially calculate the margin of error. How far can I be from the sample mean on either end, that I am still within that confidence level, that I'm still 90% confident that I'm within this range, that the true population mean is within this range, and that's how I find the confidence interval. So at a 90% confidence level, the interval is between 22.3 and 23.5. I am 90% confident that the true population mean is going to be within that interval. Okay? All right. I hope that's clear. I mean, so if you work through a few examples, and there's many of them, many questions um, on the homework to give you enough practice doing this, you should be able to see what's going on here. Okay. So interpreting the numbers, I mean, you'll find a few things here that I want to emphasize. The first thing is that the population mean is a fixed number. If we could study the population as a whole, the average inside that population is a fixed number. That fixed number is either inside the confidence interval or it's not, right? That's what it means, right? So it's incorrect to say that there is 90% probability that the actual mean is inside that range, right? That's not what it is. Because either mu is inside the range or it's not. So to say there's 90% probability that mu is within that range is kind of the incorrect way. The right interpretation is that if I take a large number of these, if I collect multiple different samples, form confidence intervals using each of those samples, then in 90% of those confidence intervals, the true mean will be, so it's like I say, for that 90% confidence interval, I collect the first sample and I form the confidence interval. Then I collect a second sample and I form the confidence interval. I collect the third sample, I form the confidence interval around it. Fourth sample, I form the confidence interval. What this means is that if I conduct this um, exercise multiple number of times, in about 90% of this confidence intervals, the true mean is going to be in going to be within that range I've defined. In about 10% of them, so 9 of them, the way drawn it here, out of these 10 confidence intervals I've formed, in 9 of them, the true mean is going to be within that range. In one of them, it's not going to be, right? So about 10% of the time, in the very long run, 9 of every 10 such intervals will actually contain the true population mean, and one of them might not. Okay, that's what it means to be 90% at the 90% confidence interval. It is not that with 90% probability that the true population mean is found within any particular confidence interval. It says that if you form a whole bunch of different confidence intervals, about 90% of those confidence intervals that you form will contain the true population mean, and about 10% of them will not. Okay. The last thing that I want to talk about in this section is to basically talk about for a given level of confidence, if I have to have a particular level of confidence that I have in mind, what is the minimum sample size that I need to collect for me to be that level confident in the estimation, right? So the minimum sample size is given by ZC times sigma over E squared, right? So this is coming from this formula that E is ZC times sigma over the square root of n. Right? So the margin of error is ZC times sigma over the square root of n. So if I had to get n here for a given margin of error, I can just rewrite this. So I take if I do this, sorry. So the square root of n here would be ZC times sigma over E, and then I square both sides, and then I get n is equal to ZC times sigma over E squared. Okay, so from here I can just, let's come back to this form. So it's not some new formula, it's just a rewriting of the formula for the margin of error. But in this case, we are interested about the sample size, not the margin of error. So for a given margin of error, for a given confidence level and a given margin of error, what is the minimum sample size that I need to be that level confident in the analysis, right? All right. So for instance, here's an example on how to determine the minimum sample size. You want to estimate the mean number of friends for all users of the website, right? So you have a particular website and you want to find the average number of friends for all the users of your website. So what do you need to do is that go collect the sample so that you can get a sample statistic. How many users must be included? Must be included in the sample, which is a way of saying what should be the minimum sample size if you want to be 95% confident that the sample mean is within 7 friends of the population, and assume that the sample standard deviation is given to be about 53. Okay, so we are defining the margin of error ahead of time. We are defining the confidence level ahead of time. And for this level of confidence, for us to be within this margin of error, what is the minimum sample size that is required for the analysis to go through? Okay. So, so what do we need for this? First of all, we want to be 95% confident. So if we want to be 95% confident, we need to be within this range of Z critical value. So if this is 95%, the remainder is 10%, 5%. So 2.5% here, 2.5% here. So I would go out, look up 0.025 in the standard normal table, and then I would come up with the Z critical value of negative 1.96, and here it will be positive 1.96. So Z critical is 1.96. So once I have Z critical, and I know the standard deviation, which is 53, and I know my margin of error, which is 7, then the minimum sample size is ZC times sigma over E squared, so 1.96 times 53 over 7 squared, or 220.23, which tells me that for me to be 95% confident that the margin of error is within 7 friends. Given that the standard deviation is 53, I need a minimum sample size of at least 221 users inside the sample. Okay. So sometimes when you ask the question, okay, how do I know how large a sample to collect? Right? If I'm able to collect only one sample, and if the question is, all right, how large should it be? What is the minimum sample size? You can say, okay, let me think about my error tolerance, what my margin of error should be for the analysis, and at what level of confidence I want to conduct the analysis. So if I know those two numbers and I know the standard deviation, then I can estimate what the minimum sample size needs to be. Okay. All right. So that's basically all there is on the first section in this discussion, where we are trying to find confidence intervals for the mean. This is the case where the population standard deviation is assumed known. This is how you would calculate the confidence interval and find the minimum sample size. All right. So as usual, if there's any questions on this, please leave them in the comments below the video, or send me an email, or see me in office hours. I'm happy to help. And so I'll stop there for this discussion, and then I'll see you in the next one. All right. Okay. Thanks for watching, and good luck.